All right, so this is group number 5. If I'm sharing this video is because I never got in contact enough with my group members to actually record something, or our schedules didn't work because requiring people in an online class to record a video together is impractical. But as we continue, we can see that the first thing I did is I calculated the volume using length times width times height after converting all of these from millimeters to centimeters by dividing all the measurements by 10. After that, I then got the density for all the values by dividing our mass by the volume. After we got the density, I did the average density by adding all these up, dividing them by 4, which gave me 2.29 grams per milliliters. After that was completed, I then graphed the whole thing as mass versus volume, where mass was my x and volume was my y. After plotting the points, created a trend line, which did not include value number 4. Got the equation for the line, which is 2.74x plus 3. The plus 3 was an estimate from this point here, and 2.74 is my slope. You see here that the slope is much higher than the average density, and this is likely due to the fact that the average density included all 4 points, where value number 4 is quite the variant measurement, having a much higher volume and a lower density than the other measurements. And we'll see here on the graph that it is not included on the trend line, meaning it was not affecting our slope. So once again, these three are quite close to each other, having very little variant of like 0.02, 0.01 grams per milliliter difference, where once again number 4 is quite different and quite far away from those. And then also calculated our percent error using the slope. This is the absolute value of the density of aluminum, 2.710 grams per milliliter, minus our slope, and divided by the density of aluminum again, times 100, gave us 1.11% of a percentage of an error. And these 3 sig figs, that is the amount of sig figs that I used here in our slope equation.